In this video, I have some additional examples of using the calculator to compute combinations. Again, I'm drawing some examples from section 5.5 in the text. I'm looking at page 314, in particular number 60, which is titled Mega Millions. The problem reads, in Mega Millions, an urn contains balls numbered 1 to 56, and a second urn contains balls numbered 1 to 46. From the first urn, 5 balls are chosen randomly without replacement and without regard to order. From the second urn, 1 ball is chosen randomly. For a $1 bet, a player chooses one set of 5 numbers to match the balls selected from the first urn, and 1 number to match the balls selected from the second urn. To win, all 6 numbers must match. That is, the player must match the first 5 balls selected from the first urn and the single ball selected from the second urn. What's the probability of winning the Mega Millions with a single ticket? Well, this is most definitely a combination, and let's take 2 steps into this, or let's take 2 steps to do this problem here. The first step, let's just calculate the number of ways that there are to do the number of balls as they're suggesting. So that would be 56 choose 5. Let's key that in. Times 46 choose 1. Now, of course, if you know 46 choose 1 is 46, then you can just key in 46. But suppose you didn't know that. So you want to key in 46 choose 1. And that is the number of ways for that to take place. Now, the probability of winning that, a lottery with a single ticket, would be the number of favorable outcomes, which would be one way because you have 1 ticket, divided by the number of possible outcomes, which you can see on the screen right there. So the best way to calculate that would be to take 1 and then divide it by the answer memory register. The answer memory register always stores automatically the last calculation you did. So in this case, it has the result of 56 choose 5 times 46 choose 1 in it. And that's your probability right there. It's very, very small. And by the way, you'll notice that probability is given in scientific notation format. We'd probably prefer it as a decimal. It's very common for people to write that as just 5.69 and they leave it and they never stop to reflect that you can't have a probability higher than 1. Anyway, for the next example, I want to do number 62. This is a really nice example because it shows the versatility of the calculator here. Here's what the problem says. It says, suppose that there are 55 Democrats and 45 Republicans in the U.S. Senate. A committee of 7 senators is to be formed by selecting members of the Senate randomly. Part A asks, what's the probability that the committee is composed of all Democrats? So in other words, you want to choose 7 Democrats from the 55 Democrats and 0 Republicans from the 45 Republicans. And then you want to convert that to a probability by dividing the number of possible ways to choose 7 from 100. So let's key that in. We'll do 55 choose 7 times 45 choose 0. Now, of course, if you know that 45 choose 0 is 1, you might be thinking, well, why would you want to key that in? Well, you'll see. We're going to make an easy way of doing this question here. And then we want to divide that by 100 choose 7. And so the probability that the committee would be composed of Democrats entirely is right there, as you see, 0.01267, blah, 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 about 1.2, 1.3%. Part B asks, what is the probability that the committee is composed of all Republicans? Now, instead of retyping what we did there, we can retrieve our last key sequence and we can edit it. You do that as follows. You press second enter, and you can see that it coughs up what we just keyed in. So we can just go back here and edit this instead of having to retype from the beginning. So we want to change that now to 55 choose 0 because we're not choosing any Democrats now. It's supposed to be all Republicans. And then we want to have 45 choose 7. I missed that there. 45 choose 7. And the denominator is not going to change. So you just press enter And there's your result, about 0.0028, so yeah, about 3 thousandths, 2/200ths of a percent, if you want to say it that way. Anyway, part C says, what is the probability that the committee is composed of 3 Democrats and 4 Republicans? Well, again, we just need to make some minor changes to our key sequence here. It's going to be 55 choose 3, and then 45 choose 4. Change that to a 4. Again, the denominator doesn't change, so we don't need to change anything else. You just press enter, and there's the probability right there. One more example here. I'm looking at number 70. It's on page 315 in the text. It says acceptance sampling. Suppose that you've just received a shipment of 100 televisions. Although you don't know this, 6 of them are defective. To determine whether you will accept the shipment, you randomly select 5 televisions and test them. If all 5 televisions work, you accept the shipment. Otherwise, the shipment is rejected. What is the probability of accepting the shipment? Now, in this case, you have to understand that accepting the shipment means we're asking effectively, what's the probability that all 5 of the TVs in our sample are going to work? And so to compute that, we can do something very similar to the last example. If you think about it, if you have 100 TVs and 6 of them are bad, it means that 94 of the TVs are good. And we want all good ones in our sample, so we take 94, choose 5. And there are 6 TVs that are bad. We don't want any of those in our sample, so we'll take 6, choose 0. Now again, if you know that 6 choose 0 is 1, feel free to just key in 1, or don't key in anything if you don't want to. But anyway, I'm just keying it in for completeness sake. And then for the denominator, we have 100 TVs and we're choosing 5 of them. So the number of possible ways would be 100 choose 5. And therefore the probability of accepting the shipment would be about 72.9%. Hope that helps. Stay tuned for some additional videos to help you work your way through Chapter 6.